let's keep going. Then, so last time we covered three-phase power flow, right? So to remind ourselves is almost all transmission lines, transmission systems look something like this. You have a generator with 3 lines coming out of it. And then all this goes into a load. So this is the three-phase power flow. The reason is if you choose the phase offset correctly, you can cancel. You can achieve net zero current flow, right? So you don't need a return path for these lines. Okay. So so then since we have 3 lines, there's many voltages and many currents we can talk about, right? So if you look at the generator and the load, the generator or the load can be Y connected or delta connected. This can also be Y connected or delta connected, right? So they need not be the same collection, right? So for example, if you're a load, you typically don't know how the generator is connected. So both sides choose the best connection for them. And based on these connections, we can compute the various current and voltage and power in the system, right? So if you look at the voltages in the system, normally the voltage we use is the line-to-line voltage. Right, so normally the voltage we use for this kind of system is line-to-line voltage. Right, so this is something like VAB. The reason is this is the voltage you can measure. Right, so if you look at the lines, we can potentially measure the voltage between the lines. Where if we don't know how the generator or how the load is connected, we may not have access to the phase voltage. Right, so this is line-to-line voltage, something we talk about. So this is the convention for voltage. So if a voltage value is given and it's not stated what type of voltage it is, then we assume it's line-to-line voltage. And then for current, we talk about something like line current. We can talk about line current. This is something like IA. Right? Again, this is the current you can actually measure. Right? So if you see 3 lines, you can measure a current flowing on the line. Whereas you may not see, for example, the phase current. Right? So again, if you don't know how the load is connected, you may not know what the phase current is. Okay? So if you take the voltage to be line to line, you take the current to be line current, then our power equation, okay, so then the power, let's say P, this is √3, the line-to-line voltage, the line current, times cosine of the angle difference between the voltage and the line. Okay, so this is 3. The voltage is line-to-line. The current is a line current, and this is cosine theta. Okay, so this equation for P and the corresponding equation for Q, where you use the sine theta, this is always correct. Okay, so it's always √3 times the line-to-line voltage times the line current times the angle difference. Okay. So the reason we have this √3 sitting in front, right? So the reason we have this √3 sitting in front is the following. Suppose you have a Y connected. Right, so suppose the entire system is Y connected. Y connected generator, Y connected load. Then we can write P equals to 3 times VA, IA, cosine theta, right? Because of the whole system is just 3 copies of phase A, right? So it's 3 times VA times IA times cosine theta. And we know that the line-to-line voltage is √3 times the phase voltage. So you can substitute VAB into the above equation to recover the √3 factor. We can recover √3. As Y connected, then we know P is 3 times the phase voltage times the phase current times the, 3 times the line-to-line voltage times the phase current times cosine of the angle. But here we know IA is √3 times IAB, so this recovers the equation up top, right? So if you want, you can always just remember this one equation and use this one equation, okay, when you do the power calculations. Okay. So this is the key equation to remember. You can always figure out what the angle is, then convert all voltage magnitude to line, convert the current to the line current and use this equation. Right? And for this equation, it doesn't matter what the connection is. You can have Y delta, you can have multiple loads with different connections. This equation will work. Any questions with this equation?
I have a question about theta.
Okay, yeah.
So theta would be between, like, for example, VA and IA, right? It would not be between VAB and IA?
Yes, yes. So you're right. So that's a good point. So theta, this is the angle between VA and IA, or VAB and IAB. Right. So you can either look at the phase, right? So you can look at the, so for Y connection, this is between VA and IA. For a delta connection, this is VAB and IAB. Right. So for this course, we will always only have one generator. Okay, so the way we use this equations and the way we figure out the delta is figure out the angle. As for this class, we'll only have one generator. So the generators will either be Y connected or delta connected. Then the best way is to convert the load to be whatever the connection the generator is, and do calculations that way. Right. So since we all will always only have one type of generator connection, so there is no confusion there. Right. So suppose you got a question saying, you have a, right. So suppose the question says, oh, what if I have a delta connected generator, but a Y connected load? How do I exactly figure out the angle? Right. So this is a Y connected. The best way is to always convert this to a delta to delta connection. Right, so you can always convert the load between Y and delta. And the way, once you do this conversion, it will be sort of more clear. Should you use VAB and IAB, or should you use VA and IA to figure out the angle? So we'll be clear from the question if you need to, if the load and the generator is different, always convert the load connection to the generator connection. Okay. Any other questions about this? Okay, good. So, right. So in this class, we will not deal with what if you have, two generators, but they have different connections, and how do you do that conversion? So that's something you'll cover in 454. Right. So there is a way to systematically do this. It's a little bit, it's not that hard, but a little bit sort of tedious to do. So in this class, we're going to assume that there's only one generator. So let's do an example. Right? So this is an example where the load is a delta connected load, and the generator is a Y connected generator. Right? And we want to figure out the power consumption of this. Okay. All right, so this is similar to an example we did before. So this is the same as a example we did before. Right, so it's basically this example, right? So we're going to write down some numbers If you're confused where the numbers come from, it comes from this second example, the third example we did in this lecture. Okay, so in that example, we basically compute the current and voltage. Now we want to compute the power consumed by the load. Okay. So this power, when we have a three-phase, this means the total power consumed by all three phases. Right? So when we talk about power consumption and we have a three-phase system, we always talk about the total power. Okay? Total power. So we'll do this, let's say we want to do this calculation. There's two ways we can do it, right? So first, let's use the equation where we have P is √3, the line-to-line voltage, the line current times cosine of the angle, right? Times cosine of the angle. Okay, so when we look at this problem, we can figure out what the current is, and we can figure out what the angle is. Right? So here, let's first figure out what the voltage is. So the line-to-line voltage is the VAB voltage. This is √3 times the line-to-neutral voltage, VAN. This is 208 volts. Okay. And the current, this is basically this we got from before. We compute the current to be 72 amps. We compute the current to be 72 amps. Now for the angle, right? So we want to figure out the angle. We know if you convert, right? So we can convert this to a Y load, right? We can take this, we have an equivalent ZY for this load. And so we do this conversion. If we have this equivalent ZY, we would get as 1.67 angle 7 degrees. So this is our load. So the angle that's created between the voltage and the current is basically the angle of this impedance. Right? So P is the angle of this impedance. So we can copy this down, and what we will get is theta is basically so we compute the angle from this, so we know IA equals to VA over ZY. And here the angle is minus 37 degrees. So we have P equals to √3, V line, I line. Cosine of this angle, plugging everything in, we get 20 times kilowatt. So this is we take √3, V line, I line, cosine theta. Okay. So we can do this in another way, right? So we want to use, if you don't like √3, you want to compute everything in terms of 3. That's also okay. You can have, what you do is you have 3, the phase voltage, the phase current, times the cosine of the angle. So here the phase voltage is VAB, √3 times 120, this is 208. The phase current, this is IAB, this is 1 over √3 times IA. So this is 41.57. The angle is same as before, you get P equals 20 kilowatts. So it's equivalent, which way you do, but a √3 will come out somewhere. Okay, so you will have √3 flying around when you do this kind of questions. And you know, as long as you can keep track of where the root 3 goes, then it's fine. So my recommendation will always to use, just remember one formula. I just, you know, when you practice on homework and when you do the final, just use one formula. So you don't, you know, get confused by, you know, should you multiply or divide by root 3? Right? So if you remember one formula, you just remember this formula always converts all the voltage to line, convert the current to the line current, then the power will work out fine. Questions?
I just had a quick question.
Yeah, go ahead.
When you actually do the calculation, is theta in degrees or in radians, like it always is?
So this is up to your calculator, right? So if your calculator takes radians, then do it in radians. When you calculate takes degrees, do it in degrees.
Because I know like the right. Power equations for like the half wave and the full wave, like everything had to be in radians. So that's not the case for this.
Yeah, that's not the case, right? You're taking cosine of an angle. So depending on the convention for the cosine command. So I think in MATLAB, the cosine is always in radians, I believe. But then I know for some other programs, for some calculators, the default setting for sine and cosine are in degrees. So this is, you know, figure out whatever software you're actually using, what kind of convention it takes. So when you write an answer, right? So when you write an answer on the homework or on the final, it doesn't matter. You can pick one. Right? So as long as you're clear what the unit is. So if it's degree, you know, write a little circle. If it's radian, write radians. As long as you're clear about that, then either is fine.
Quick question.
Yeah.
So for the angle, you use for the theta, you use the thetas for the I line, right?
Mm-hmm.
You don't use the one for the load.
So the angle is always, right? So if you convert this to a y connected, then your angle is just the angle between just the angle you compute, right? So you can figure out what the current is. And you divide by zy, that's what you get for the angle.
Okay, thank you.
Yeah, so, right, so in the literature, it's a little bit more common to see things stated in angles, angles stated in degrees and not radians, because when you state things in radians, you get very small numbers, right? So degrees have a little bit larger numbers to look at. But for this class and for the exam, it doesn't matter. Just pick one instead. Okay. Right. So again, root 3 is important, right? So for this type of questions, you know, most of the mistakes is somebody, you know, you're missing a root 3 somewhere. So be off with the final solution by a factor of root 3. We don't grade it very harshly. So if you off by a factor of root 3, then, you know, you get 1 mark off from that. But again, that's you know, you rather not lose that. So when you do this kind of question, just keep track of where all this root 3 goes. Okay? There'll be a lot of root 3 flying around, but just keep track of where those are. All right, so in our case, right, so what we do is, in 3 phases, nobody ever bothers to draw 3 lines in a diagram, right? So since everything is balanced, everything is symmetrical, it's as if we have 3. That's where we have 3 circuits, right, replicated, right, or a circuit replicated 3 times. So most times we'll just study 3 phases. Okay, so I'm sorry, most times we'll just study a single phase. And we'll just pick a phase of this and study this. Right? Okay. So this is valid, for example, either star means Y connected or delta connected things. So one question that's interesting is the fact that if you see 3 transmission lines, okay, so if you see 3 transmission lines running like this, right? So let's say this is phase A, phase B, and phase C. Is this actually symmetrical? if you think about it, if you're transmitting power and you have 3 transmission lines, let's say these lines are made of identical materials, they're exactly the same dimensions and things like that. And you're running 3 lines, right, across a long distance. Is this actually symmetrical?
No.
Why not?
I'm shooting in the dark, but I would assume the inductive loads would be different because B is going to get interfered with both A and C and things like that, no?
Right. So that's exactly correct, right? So if you look at 3 wires, what happens when you have conductors with space between them as they look like a capacitor? But then there's some asymmetry between this, right? B is always in the middle. So it sees, 2 equal distance conductors, but A sees 2 conductors not at the same distance and both to one side, right? So this is actually not a symmetrical case. But then we want symmetry, right? We want symmetry to make everything the same, so we only need to analyze single phase, one of the phases. So how do we make them more symmetrical? We have 3 wires. How do I achieve symmetry? I don't want B to be always in the middle. So what do I do when I run sort of wires across long distance?
Do they change their position?
Sorry?
Change their position on the transformer poles. So
right.
Change what's on top, what's on bottom, what's in the middle.
Right, so you swap them, right? So this is called transpose lines. So what you see, again, when you look at high voltage transmission, now if you ever driving the highway and you can take a look, what happens is the lines will run something like this. So this is A. So we'll run for a while, they'll actually change position. This is A. This is B. This B will come up, and this is C. So we have 3 wires. Will be transposed this way, right? And this basically on average saying they're all symmetrical to each other. Okay, so we take a lot of effort to make things symmetrical actually in practice. Having phase balance is very important. And if you ever go work for a utility, your job may be actually worrying about this. As how do I balance the phase? How do I balance this phase? So if you can make it balanced, right? Suppose you can make it balanced, then what you can do is you can just draw 1-line diagrams. As now you don't need to draw 3 lines. Although the assumption is always this is simply a perf. No, there are actually 3 lines. There are actually 3 phases. But we're gonna just draw one of them. Alex says, does that not increase the stray inductance? So by stray inductance, you mean inductance to ground, Alex?
No, I just mean like the inductance through the wire when you're kind of looping it like
that. No, so so you have 3 wires. So if you look at the actual inductance matrix, it's a 9x9. Sorry, it's not 9x9. It's a 3x3 matrix. So it's 9 numbers. And this just makes that matrix symmetrical when you transpose them like this. It's not necessarily higher inductance. So
So like even though they're symmetrical, would it increase the overall inductance of the wire?
Not necessarily, no. Because they don't have the same inductance. So if you don't transpose them, B sees fairly high inductance, right? Because you have 2 wires that are sort of close to it. Where A and C will see lower inductance because you have a wire that's far away. But the problem is, so when you transpose them, it is true that for inductance for A may go up, but for B it goes down. So it's hard to say in total whether it goes up or down. So it's a more rebalancing issue than whether the absolute number goes up and down. Okay, so this is again something you would see in a lot more detail in 454. Although for now, it's suffice to know that there where we go to everything we can do to make it symmetrical, we'll do. Right? So there's a lot of painstaking for this. So this allows you to draw a one-line diagram. So most diagrams we see is like this. Again, the assumption is that there are 3 lines. And we just don't bother to draw them. And if you look at a bigger diagram, looks something like this. Okay, so if you look at this phase balancing and the one-line diagrams and stuff. So when you think about your house, how many phase do you think your house gets or your apartment? Do you get 3-phase power or single phase?
Single.
Single. Most likely your house is single phase. Although our building is 3-phase. So I mean, my office, like the ECE building is actually 3-phase because we draw a lot of power. So big buildings, maybe 3-phase, we're 3-phase, but houses are single phase. So how do you do that balancing? So each of you has a single phase load, but then my utility to the transmission grid, I want to look like a balanced 3-phase load, right? Because the whole thing is designed and us being balanced. So how do we do that?
Get different groups of houses to be on different phases, so it's roughly balances in aggregate.
So roughly balancing aggregate, but how do we make sure it's for balance from in real time then? So you don't get unlucky. One group of people are not home in one area. So when we design it, we'll design the phase to be roughly balanced, right? We'll put roughly same number of people on each phase. But in real time, what do we do?
Switching?
Right, we do switching. So a lot of times in distribution system, switching is to balance the phase, right? So you don't have to switch too much. The areas are big enough that you have good aggregation, but sometimes you do a little bit of switching to make sure they're balanced. And one interesting fact is that for a lot of distribution systems, we actually don't know what house is on which phase. Right? So if you go to City Light, they may not be able to tell you your house is on phase B or A or C. Sometimes we don't know. So this is actually a challenge as more things like, say EVs coming to the grid. As we want to balance the load, right? Because the transmission network wants a balance load. But then sometimes we don't know even which phase you're on. So balancing or doing sort of fine-grained management can be difficult. We don't know which phase you're on. So this is an interesting question that utilities are experiencing. So, when we designed this, we just want them to balance. We didn't bother a lot of times recording what is on what phase. But nowadays, there's a lot more control opportunities, right? So, if everybody on phase A decide to buy a Tesla, that's probably not so good. Right? But then utility may not even know which phase this thing is on. So there's sort of interesting challenges coming up in the grid, where before you just make sure they roughly have the same number of houses. Nowadays, there's sort of more granular information start to matter. So there's always a challenge for utilities to figure out what exactly is going on in the network. So that's something to keep in mind as we try to balance this, but this is becoming somewhat more challenging as more different types of loads come to the system. Okay. Any other questions about 3-phase? Okay, so this is what we'll say about 3-phase. Most problems come down, we'll ask you to compute power. So the thing to watch out for is just again, make sure root 3 goes to the correct spot. So the next thing we'll cover, this is 3-phase transmission. So next we'll go into generation. Right, so we'll talk about synchronous generators. So this is again something you will do in your lab. So we'll talk about synchronous generators and motors. So this is the next topic. So we're almost to the end of the quarter. So the next 3 topics is we have synchronous generators, which is the most common generators, but is mathematically simple or simpler than the other things. Then we'll look at transformers. This is slightly more complicated. Then we'll look at induction machines. Okay. So these are the big topics we have left in the class. We'll see how much time we get. If we have some time at the end, we'll go to blackouts. So we'll talk about things that can go wrong in the grid, right? So, but this is a plan. This is the next 3 topics we'll cover. So synchronous generators. So what does synchronous generator mean? Where does the word synchronous comes from? So before that, actually, that's one thing we should all remember. One thing that's important is when we talk about generator and motors, there are actually physically no difference between the two. They look the same. They're the same machine, except one as you are turning the turbine, you're generating power for generator. For a motor, as the turbine is being turned because you're putting electric power into it, and this is doing mechanical work. Other than the direction of power flow, everything else is the same between the two. Okay? So very often we'll call this just machines, synchronous machines, because it doesn't matter we differentiate between generator and motors. It's the same piece of equipment that we talk about. Okay? So now sometimes we'll see generators, sometimes we'll say motors, sometimes we'll say machines. They're the same thing. Okay, so machines is a catch-all term. And then motor generators, you can think of as a way to specify which direction power is flowing, right? But they look the same. So when you have a electric vehicle motor, it can run backwards, right? There's no fundamental limits to there's no difference. There's nothing different when you run a motor one way versus you run a motor the other way, at least from the machine's perspective. So yeah, go ahead.
Sorry. So is that why regenerative braking works on like electric cars? Is that basically what they're doing?
Yeah, so regenerative braking works because you're running the motor backwards. So running the motor is not hard in that. It's sort of more of the battery power flow and charging and discharging. That's a little bit harder. But the machines itself is quite simple. Just literally it's the same thing. You don't need to do anything to the machine. Yeah. Okay, so this is like if you have electric bikes, some of the bikes, specialized bikes, you can pedal to charge your battery. If the electronics allows it, you can do it. Right? It's as if the battery is helping you pedal the bike. It's the same thing. So this is the machines we have. So if you look inside the machine, it's quite simple. It's quite simple. Basically, we have a stator, right? So here I'm showing a 3-phase. It's all generators are 3-phase that we have. And then you have a rotor. So by the name, as the name implies, this rotor will turn inside the stator, and that's the way you generate electricity. You generate power, electric power. So you put this thing inside of it, something turns it, and you can generate the current and the voltage and power that way. Okay. So the reason this is called a synchronous machine, is the fact that this omega s, this angular frequency, this angular frequency is set by the generator itself. Okay, there's no reason to you don't need a existing field to do this. You can turn the rotor at a speed, omega s, that you want. Then that's the frequency of the sine wave that will be generated. So synchronous means I can set my own frequency. Later, we'll see for induction machine, this is not the case. Okay, it turns out for induction machine, you cannot set your own speed. But for synchronous machine, you can set it. So for us, it's 60 Hertz. For Europe, again, it's 50 Hertz. Right? There's nothing magical about the number 50 and 60. It's just the way we happen to pick those numbers. So I guess one reason we can think of is, why did we pick 50 or 60? Like, we could have chose other numbers. Anybody remember what the reason for that was? I have a guess, like, why not 20? Like, why not 100? Why did we settle on 50s and 60s for frequency?
Is it something to do with what the actual like turbines can handle?
That's a design speed. Also, there's gearboxes. So I guess, so let's think about the low speed. So why is something like 10 Hertz not very good? So if I change our, if we change our frequency to 10 Hertz, what would you notice?
Our lights would be noticeably flashing. I don't know.
Right, so your lights will flicker. So if you have a light, just a resistor, so the light will flicker. So it turns out humans are, good at noticing things under 30 Hertz. 60 Hertz, we don't really notice. So our lights, light bulb will flash at 60 Hertz, but that's something we don't notice, right? So too low is not good, right? So anything under 30 or 40 was actually noticeable by people, so you need to be higher than that. Then 50 was picked because it was a nice round number. Having a too high of a speed, as you said, makes turbines hard. These are big turbines. So turning that thing at 100 Hertz was challenging. So people first settled on, okay, let's pick a round number as about 40 Hertz, 50. But then there was some competition, and one way to differentiate yourself at that time was to pick a different frequency. So it was I forgot whether it was GE or who did and pick 60 as their convention. Then it just turned out the way that people adopted different standards. Okay, so that's the reason. There's no reason why 50 or 60 is better than the other, but it just happened. People pick slightly different frequency at the start, then different countries adopted different frequencies. So one has 50, one has 60. But then again, the reason you can pick these generators will generate. They can set the frequency. They can rotate at 60 Hertz or 3600 RPM. They can rotate, and again, these are big machines, and these are the big generators, and they generate 3-phase power like this. So then if we look at the model, if we look at the mathematical model a little bit, let's look at the three things that's labeled here. One is this internal this phi f. And then let's look at this current and this voltage VF. So what we want is we want to model this in an equivalent circuit. We want to model this in an equivalent circuit. So if you have a rotating magnetic field, which is the thing we have here, for VF, then will look like a AC voltage source because the derivative of the magnetic field is the electric field. Okay, so if you rotate this at constant speed, you will have an AC. You will have an AC source, right? So this is AC voltage source. So given this AC voltage source, right? So the frequency of the source is set by this rotation frequency. Okay? This rotating frequency, omega s, sets the frequency of the AC source. Okay? So the frequency of EF is So this internal EMF, this is EF, is omega S. This is basically how fast you turn. How about the voltage or the magnitude? How do I change the magnitude of this?
Number of windings?
Number of windings is one, but if you look at the DC source, right? So this is proportional to VF or IF. Okay? So what this VF is, this is called exciter. So this is called the exciter or excitation voltage. This is called excitation current. Okay, so this comes from a small DC source. If you want, you can think of the battery as providing some current through the windings. Okay, and this current through the windings basically sets up the size of the, or the magnitude of the EF. Okay, so they do not produce power, right? The power is not coming from the excitation current. This basically sets a voltage level. The actual power comes from the mechanical power that's turning this turbine. Okay, so we have exciter. Basically, you can control your own voltage, right? It's our voltage control. Okay, so the equivalent circuit model is this is some generator, some AC voltage source, right? Where we can to control the voltage level and to some extent the frequency. Although we don't want the frequency to change too much, but right, so that's the circuit we have. Okay. So this rotor, once it turns, looks like some source like this. So then to complete the model, right? To be a more complete model, what we have is this is our AC voltage source. We have AC voltage source. Then we have this voltage source sitting behind a reactance XS, a resistance R. Okay. So this is what VT. VT is this is called the terminal voltage. So terminal voltage means this is the voltage you'll see when you look into the machine, right? So things like XS and R are internal to the machine. They're not really something, right? They're representations of something. So when you look into the machine and you measure the voltage, you measure something that's VT. Right? You may measure this VT value. So if you look at this equivalent circuit, where does XS come from? Why is there some reactance if you look inside, if you look into the machine?
Because of the windings going around and the current, right? Current going through windings creates a magnetic force, which is going to create inductance.
Right. So anytime you have, right? So that's correct. Anytime you have windings of wires, right? You have windings of wires, you have inductor, because that's actually how you make an inductor. Right? So they look like inductor. They show up as this reactance. And so this reactance you can think of as sort of the term, the representation that lumps all these coils of wires together. This is our XS. This is called the synchronous reactance because this is a reactance that's coming out of the generator. Then this R as a resistance, again, is because nothing is ideal, right? You're passing currents through all these wires with some resistance going on. But normally what we have is R will be less than equal to XS. Okay, the resistance will be very small compared to XS. So normally we don't need to worry about R. Right? So the resistance inside the generator is tiny compared both to its own synchronous reactance and the other resistance in the grid somewhere else. So R is almost never considered when we look at a model. So this gives us our equivalent circuit, which is a very standard circuit. We have, this is XS. We have some terminal voltage VT. We have some equivalent field voltage. And then we have a current IA, right? So this is again a single phase equivalent or single phase representation. Okay, so we'll be multiplying by 3 later, because again, this is a 3-phase circuit, but we'll only draw the single phase. All right, so then a key equation to remember is how do you relate EF to VT? Okay, so we want to relate this to. Because EF, right, so if I'm trying to control what the generator is, right, so my control comes from my ability to control EF, because I can boost its magnitude by changing the excitation current. But from the rest of the grid, they only see VT, right? So the grid, when the grid looks like at the generator, it sees VT. That's the only thing it sees. It doesn't see EF directly. EF is sitting behind this reactance. But from a generator controls perspective, if I want to boost the voltage, I'm actually boosting EF. I don't get VT directly. I don't get control of VT directly. Right? So the equation relating this two is, very important. We'll often use this equation. We'll use this equation a lot. So it's a simple equation, right? So if I write EF is equal to VT plus what? How do I relate this to? How are the voltages related?
XS times IA.
Right, so this is J XS times IA. Right, so we're going to take XS to be a real number as an inductor, so we have J in front of times IA. Right, so this is a good equation to remember. Right, this equation shows up everywhere for synchronous generators, and this is still important when we do sort of modeling of generators. We often have to deal with this equation to sort of relay the outside of the generator to the inside of the generator. So this is our circuit, right? So important equation to remember. Again, the power comes from the fact that we have a prime mover. So this is, you can think of what the prime mover is. This is a shaft on the turbine. This is a thing, the mechanical thing that turns the rotor. So what we have is, this is mechanical energy that turns through a prime mover, wind or hydro or conventional generation. And this shows up from a grid perspective to be this internal EMF. This EMF goes through a synchronous reactance. And then from the grid's perspective, the grid sees some terminal voltage. So if you're a load, you see this terminal voltage. Okay. So we're not going to cover what happens, between the prime mover and the generator. That's actually a very complicated electromechanical system. What we're going to focus on is this part of it. Okay. We're going to look at what happens once you convert it into an equivalent circuit. Okay. So there are a lot of synchronous generators out there. This is, for example, one picture of it, right? So if you need a backup generator, this is, for example, a type of backup generator you can buy. This is a synchronous generator. It uses diesel, for example, to turn the prime mover, and then that generates power. Okay, so this is quite most generators we have today are synchronous ones. Most generators we have are synchronous ones, with some exception being that for some wind turbines, you'll find induction machines. But for other generators, it's synchronous. So we'll get into a lot more about these equations, about this equation, basically. So for now, let's take our break. Then at the 3:33, we'll come back and we'll look at the sort of other equations in terms of synchronous generator. The equation turns out not to be very hard because it's a simplified circuit. The circuit is quite simple. But so we'll go through in how to compute power, how to compute current, what is the maximum power you can generate, and things like that. Okay, so let's come back at the 3:33. Okay, so let's resume with synchronous generators. Right, so the generator itself is easy to build. We've been building synchronous generators for the last 100 years or so. So you can buy this, off the shelf from some store as a backup generator for your home. The more interesting question is, if you buy this generator, right? If you buy this generator, if your load changes, what does your generator do? Right? So let's say you bought a generator and there's power outage and you're powering your home at this load. And then, let's say your load keeps on changing, you turn on and off the light. So what does the generator do? Well, there are basically two control loops inside this generator. One is the generator will try to change its excitation current to make sure that you see a constant voltage. So this tries to maintain a constant voltage for the load. Right? For your home, may try to maintain 240. And then what another control loop does is trying to maintain a constant frequency. So the way it maintains constant voltage, it's changing exciter current. The way it trying to maintain frequency is actually trying to adjust this valve to say how much fuel is going into the generator. Right. So by changing how much fuel or fluid I have into the generator, I can change how much power, how much mechanical power I'm putting into the generator, and that helps me maintain a 60 hertz. Right? Help me maintain 60 hertz. Okay. So this will come back to be important. So again, making a generator, like the physical parts of a generator nowadays is very standard. They're not much hard to think of some innovation that happening there. But these control loops are much more interesting. These control loops are much more interesting to think about. Okay. So the exciter, right? So the voltage control comes from the fact that if I turn off a light, your equivalent resistance for this load changes. So you want to change the voltage a little bit of the source to make sure the terminal voltage stays constant. Now for this turbine rotational speed, right? So let's think of, if you have a turbine, if you have the rotor rotating at 60 hertz, and your load increases, then what happens to the rotation speed? So let's say you suddenly add some load to it. You have this thing rotating at 60 hertz. Then what happens?
It's going to slow down.
It will slow down, right? So it's, if your load increases, something has to provide that power. So then you basically borrow from the inertia you have in the mechanical inertia you have in the rotor. And then because you slow down, the valve will do this detection and realize you need more mechanical power. So the valve will open up more, you get more mechanical power, so you recover the frequency back to 60. Right? So why the similar thing happens, if you speed up, then the valve will close, you have less mechanical power, you slow down back to 60. Okay, so these are sort of the two very important control loops for a generator. And turns out you can do a lot of things with these control loops. A lot of research is actually not so much about making the generator itself. It's more of, what do I do with these two control loops? And these Go ahead.
What does it do with the 3 phases? Because you said our houses run on 1 phase, but these are all generating 3 phases, right?
So if you buy this for a standalone generator, it's probably a single phase, or there's a setting you can pick to generate 3 phase or single phase. You can basically, to get to a single phase from a 3-phase generator, you can disconnect 2 of the lines and get a single phase output. So when you buy this generator, depend on what your load is. You can either buy a single phase generator, or just buy a 3-phase one instead. Disconnect 2 of the phases. These are different settings you can pick. Okay. All right. So if you look at these control loops, right? So there's some interesting cybersecurity thing going on here, because I can easily make the whole thing unstable, right? By hacking this. Right? For example, I can reverse the sign of the feedback controller. So when when the load demands less power, open up the valve, shoving more power, right? And then blow the generator up. Basically, that's one way to do it. And people have done this. People sort of have targeted cyber attacks where they hack the controller on one of the valves. Right? They basically hack this feedback controller. Right? So these controllers are right now they're hard to hack because they are not wireless. So if you hack them, you have somehow get the physical access to the microcontroller itself. And once you get there, sort of this, that's the hard thing to do. As for commercial generators, you can get there. Right. So then, right. So but then as we move to people saying Internet of Things, more control capability, more wireless controllers, then that's an interesting sort of cybersecurity question for what happens to these control loops. Okay. Right. So the question John has is 3-phase is more efficient. Yes, 3-phase are typically more efficient than single phase. But then if your house is single phase, then it's single phase. Right? So if the load is 3-phase, it will be 3-phase. And for commercial for big generators, it's almost always 3-phase. All right, so the model for our generator, or if you look at the circuit, so if we write, so we have a voltage source EF, XS, the terminal voltage here. Then since these will all be complex values, right? These are all phasor quantities. And we have a current. So here what we do, so it'll be useful to pick a convention for which one has the reference angle being 0. Right? So that's the convention we need, is which one has the reference bus. So normally we'll take the terminal voltage. We'll take the terminal voltage to be the reference bus. So this will be angle 0. This is the reference. Then the current will be I angle theta degrees, or theta 0 degrees angle theta. And then the EMF, this is E delta, angle delta. Okay. So here what we have is, right, so the power is VI star. Right? So this depends on, so the cosine of theta angle is important. Right? So that's just a convention. We'll choose the terminal to be 0 degrees. And so therefore the internal EMF actually has an angle and not 0 angle because it's not the reference. So when we connect this to the load, then again, as we said before, it has 2 jobs: keep the frequency constant and keep the voltage constant. So that's what the generator wants to do. You want to appear as a perfect voltage source. Right? You want to appear as an ideal voltage source to the load. So then now it's just a standard calculation, right? Of what happens when you are in open circuit, what happens when you have a resistance load, inductive load, capacitive load, answer this mixed load. Right? So if you have open circuit, then of course the current is 0, and then the internal EMF voltage is equal to the terminal voltage. You deliver no power, right? You don't deliver any power to the load. A little bit more interesting is what if you have a resistive load, right? We have this load. Then let's compute what the current is, right? So the current is V over R. So this V always has angle 0. So then I is I angle 0. Okay. So there's the angle for the current is 0. But if you look at the internal EMF, if you look at this value, this does not have a 0 angle, right? This does not have a 0 angle because this is behind the reactance. So if this is E angle delta, is the angle delta positive or negative for this case?
Depends if it's reactive or inductive, right?
So for this specific example, is it positive or negative? If it's a resistive load as the output, and it's sitting behind the reactance, right? So this is inductive reactance. Is it positive or negative?
Negative.
Right. So I'm adding, right? So here the picture is, this is angle 0, right? This is my V. This is angle 0. Ji is a real number. So JXSI, this is a real number pointing up, right? This is JXS times I. So my angle, this delta is positive. This happens to have a positive angle. So this is just an example showing that your angle for the EMF, for the E voltage, is not 0 when you connect a resistive load, right? So the angle that's 0 is a terminal, that's 0. Right, so of course here P is just I squared R. Or V squared R, Q is 0, you don't consume any reactive power. So if you're supplying purely resistive load, right? If you're supplying purely resistive load, basically if the load changes, right? So if say load increases, that means this is equivalent to R decreases. Right, so load goes up, but drawing more current. Then here, what we do is you change the mechanical power input, right? You change the mechanical power input to match the load. You change the excitation. Keep V constant. Okay. So when the load changes, you do some feedback control to make sure it still appears as an ideal voltage source. So of course we can supply a purely inductive load. So we can supply this. So here for pure inductive load, the current is V over J XL. Let's say this has a value of XL. Okay. So this is V over XL, angle minus 90 degrees. Okay. So then Here, the internal EMF field, this is plus JXS times the current. The interesting thing here is this J will cancel out the J in current, right? So this is V plus JXS, V over XL, angle minus 90 degrees. This J is angle plus 90. So basically the angles cancel out and the delta angle, this is 0 degrees. Okay. So this means that you're supplying some reactive power to the load, right? And the way you supply reactive power is, turns out your internal EMF appears to have angle 0. Okay, so this is inductive load. So the inductive load, what happens if you supply inductive load is if L changes, there's no change in the mechanical energy input, right? Because the inductive load really is not drawing any, inductive load really doesn't draw any real power, right? So you're not doing work, so there's no mechanical power input. Thus, as your E changes to match the load. So your E changes to match the load, but your mechanical power cannot change. Your mechanical power doesn't change. Okay, so here you're supplying reactive power. For a capacitive load, it's the other way around, right? So here I have, so this is similar to before. I is equal to J omega C. So V bar, this is V bar over minus J. So I is XC. I is V bar over minus JXC. Okay, so you have all these sort of equations. So here was basically the generator may absorb reactive power. Okay, so this machine could both deliver or absorb reactive power. It's not limited, right? This is not limited to only generate reactive power or only absorb reactive power. So the active power for a generator is normally positive, but then the reactive power output can be both positive or negative, depending on what the load wants to do. So a generator, the Q output for a generator can be, either positive or negative, okay, depending on the situation. Right? There's no set sign with this Q.
When we say absorb reactive power, does that mean like there's negative reactive power?
Yeah, there's negative reactive power. You may, right? Because your capacitor, you can think of, some ways as outputting a positive reactive power. So if XC, for example, is larger than XS, you have more reactive power, right? There's a net surplus of reactive power outside the internal voltage. So that reactive power has to go to the generator. So you're absorbing reactive power. But then again, this is very different than the active power. This is more of basically saying that you can change your phase offset to cancel reactive power. You're not delivering more work out of this. Okay. But the reactive output of the generator could be negative.
And does the amount of reactive power impact the amount of active power that the generator produces?
Right. For the generator, for this type of generators, normally no. Reactive power comes from how far phase offset you can be. Not normally for this type of generators does not impact how much active power you can generate. It's sort of separate rating on the generator. So it's not unlimited, right? It's not infinity, but it still is not. So how much reactive power you're absorbing typically does not impact how much active power you can generate.
Are there any other downsides to having a lot of reactive power, like with efficiency or anything?
Not from the generator's perspective. Transmission line may have a finite capacity, right? So your transmission line may not be able to carry this much apparent power, but from the generator, not really.
Okay, that makes sense.
Okay, so right, so generator can do both, right? So when you do a question, and turns out, generator is generating negative, something reactive power, that's fine. That's not necessarily doesn't mean you made a mistake. It could be negative, depending on exactly what the load turns out to be. Okay. So, at the end is, if, we can draw a generator that has a RL power, then of course, this side, the calculation is still quite simple. I is V over R plus J omega L, right? So and then this, you will have some angle. So there's really not a much, not an easy formula to have here, but you can simply follow along the sort of basic equation we have to figure out what this internal angle is. Right? We can supply the load, RL base load, internal angle. So in this case, both P and Q will be positive, right? So in this case, we have P will be larger than 0, Q will be larger than 0 because this is RL load. Yeah, questions? Okay, so so then again, this is for a load isolated generator. Right? So it supplies active power, provide or absorbs reactive power. Right? So if a generator, you have a load that's capacitive, that's fine. The generator will work fine with a capacitive load. Okay. So let's do an example to see how these equations work. So this example says we have a 3-phase Y-connected synchronous generator, supplies 6 megawatt of active power. The angle between the voltage and current at this angle, and the synchronous reactance is 6 ohms. Compute the magnitude angle of the internal EMF E. Okay. So this is our question for us. So the first thing to observe is this is the 3-phase power, right? So the single, right? So for every circuit we'll be looking at is a single phase circuit. So the first thing you do is you say, there's 6 divided by 3, 2 megawatt of per phase. Right? So we're only looking at a single phase circuit. We're going to look at how much power a single phase is carrying. Okay. So this is our voltage. This is our power. What about the voltage here? This says 25 kV. But what voltage is this? Right, so when you see a 25 kV, can I directly plug in 25 into this terminal voltage? Is this value just 25?
It should be line to line, you said, right?
Right, this is line to line, right? So the thing to remember is this 25 is line to line. But this is the Y-connected generator, right? So, and we're looking at per phase calculations. So the actual voltage for us is actually 25 kV divided by √3. Right, so this is 14.43 kV This will have angle 0 because we take this to be a reference angle. This is 14.43 kV. So this is something to always remember, right? This is something to always remember. And when you see a voltage, now you want to plug, this voltage into the equations, but this is a line-to-line voltage. So divide by √3, convert to phase. Then we know the power is VI cosine theta. Okay. So we can get the magnitude for I. So this is 2 megawatts, and we know V, so I is 173.2 amps. We're told the angle is 36.87 lagging. So the complex current is 173.2 angle minus 6.87 degrees amps. So now we're close. Now we have to use our equation. This is so it's the same question as above. This here what we have is E is V plus JXS times I. So here 6 ohms means per phase. So in this kind of questions, when you say the reactance is 6 ohms, means a per phase reactance is 6 ohms. So that's now just plugging all the numbers, 1 point. And you do the calculation, you got 15.076 angle kV. Okay. So this is the magnitude and angle of the internal EMF voltage. All right. Okay. So this is what a standalone generator looks like. So of course, most generators are not standalone. They don't just power one load. They go to the grid. They go to the grid. So let's say I have a generator. So I want to connect the generator. Right. So I have a generator. I have a circuit breaker. I want to close the circuit breaker so the generator connects to the grid. What do I have to make sure happens in the generator before I can connect to the grid? Like, what do I have to be careful about? Before I close the circuit breaker, what things should I look out for in the generator? If I take a generator, can I just connect to a grid?
Make sure it's at the right frequency.
Right, so the frequency is important. Right, on the same, when the voltage is important, right? You don't want your voltage to be very far away from the generator. Okay? So why is that if you have a wrong frequency, it's very bad for the generator? So let's say I have a 60 Hertz generator, and now I want to connect to a 50 Hertz grid. What happens to my generator? Like, why is that a very bad idea?
It's gonna blow it, won't it?
So why does it blow up?
Because the frequency is so off that it's gonna mess up the voltage that it's putting out for RMS, right?
Related, but there's sort of a, I guess, easier explanation or more intuitive one. So what if the frequency is very different? And what happens to the, right? So we said the power delivered is cosine of the angle, right? It's sort of, it's the angle depending on the angle difference between the voltage. So if your frequency is different by 10 Hertz, your angle basically changes very rapidly. right? Because your frequency is, remember, frequency is the time derivative of the angle. So if your power flow depends on the angle, and your angle is changing at something that's 10 Hertz, basically you have this sort of huge change in power flow, and that no generator can work with that kind of changing angle. Okay, so a slight difference in frequency causes the angle to run away from each other. That's why we often want the frequency to be to 60 Hertz, everything to, we want the frequency to be very close between everything in the grid, so angles don't run away. And then if it differs by 10 Hertz, then this thing sort of, the generator blows up almost immediately because the angle goes all over the place, trying to deliver power sometimes, trying to absorb power sometimes. And this is, unstable behavior for the generator. Okay. And so if some of you remember to the earthquake, the Japanese earthquake, maybe 10 something odd years ago. And then, there's big power outages in Japan. And turns out Japan is the only country, one of the few countries that has a both 50 Hertz grid and 60 Hertz grid. So, but if there's power outage, there's no way to connect the two grids. It's just impossible to connect the grid. That's both, 50, that's at such different frequencies. And similarly, this is the reason why the US is, we talk about the US is divided into 3 grids. Why you cannot just build a line between 2 grids, between, let's say, the Eastern and Western interconnection. Just build a line to say exchange some power, as these 2 grids are not frequency synchronous. They both operate a little bit around 60, but they're not trying to hit the same frequency. So if you connect a line between them, and the frequency on both sides of the line differs by, say, 1 Hertz, then bad things will happen, right? So that's why sort of this, you have to make sure the frequency is roughly matched. We'll connect anything to the grid. Okay? So the generator matters, right? Generator matters, right? So for a generator, the frequency matters a lot when you connect to the power system. So then the way we're gonna view a generator to a grid is the following. Right, so I have grid on this side, and then I have a generator on this side. What we'll assume is that the generator is small compared to the grid. So what this means is the grid sets the voltage and the frequency. Okay, so if you're a generator and you connect to the grid will set the frequency and the voltage you should work with. So then what the generator sees is generator sees a grid as a ideal voltage. Okay. So what the generator sees is the grid just appears to be something that's at a fixed voltage and a fixed frequency. And your job is to work with that fixed voltage. Okay, so this is what the grid is called an infinite bus. Okay, so this just means something that's very large, right? Where that's something that's the voltage and the frequency of the grid is not something an individual generator will change. Okay, so this is our picture, and this is often, people like to show this picture as, think of a synchronous generator as, a gentleman on a bike, right? So each individual cyclist must go with a system frequency, right? So even though the entire system depends on all the generators working together, but what happens is you can, from an individual's perspective, you can view the rest of the system as a bus that's at a fixed voltage, right? So you do impact it, and the voltage is set by all the generators together. But from a modeling perspective, for a single generator, the grid appears as a very large voltage, right? As a sort of very stiff bus, as a very stiff bus that we're not going to impact the grid operations. So this means that for operation of a grid connected generator, right, is that a generator do not give power to a particular bus, to a particular load. Okay, that's not what a generator does. Generator feeds power into the grid. Then the power is distributed. Okay, right? So you cannot say, I'm a generator, I want to power that load, right? I want to just power this particular load. I don't want to give power to other load. That's not how the system works. As you inject power into the grid, and then power flows according to Kirchhoff's laws. You don't have fine-grained control. So this is what sets the power system apart from something like the internet, right? If you are on the internet, then there's a very clear source and destination of a packet, right? So we're on Zoom, right? So, I'm talking, and the internet transmits this packet information to each of you. It does not broadcast to other people, right? So there's a specific destination and this specific source and destination pair on the internet. On a grid, there is not. There's no way to say, I want to give 50% of my power to that load, 10% to that load. You don't get to control that. You inject into the system redistributes the power. Okay? So, so sometimes you'll see that, if utility comes to you and say, oh, I can make the power you get 100% renewable. It's iffy what that means exactly from a technical sense. Right? Also, if you follow Bitcoin, there's some news on Bitcoin as how much is the power spent mining the Bitcoin renewable or not. That very much depends on where you're mining the Bitcoin. Right? There's no way to say, I built a wind farm. I just want this wind farm to mine Bitcoin. Right? That's not how the system works. Okay, so that's something to remember. So Alex asked, do you need to match phase of the generator? You can match, yeah, so you need to match the phase, or you need to make sure the phase is not off by too much. So phase matching is fairly simple, right? We're very good at measuring phase. So that just means that, so we're very good at measuring phase of AC signal. So you can think of, if you want, a phase lock loop. If you figure out what the phase of the grid is, then it's just the sort of matter of changing your rotor phase, right, to time it such that you match the grid. You can do that through several cycles. So you cannot change phase immediately, but it takes a few seconds, you can match phase to the grid. Yeah. So measuring phase from the grid is not terribly challenging nowadays.
So you said the US grid is broken into 3 sections. So if we all are running 120 volts at 60 hertz and variations by that little bit are bad, then how are they all running separate and why aren't they all just run the same thing?
Sorry, so we're all running 60 hertz, right? But we may be running at, let's say, 59.5. The Eastern interconnection may be running at 60.5. You do not want to connect these two grids together at this point. 1 hertz is big enough of a change. Right, so within our Western interconnect, our frequency is fairly balanced. So your frequency is probably very similar to a frequency that's in San Diego. Right? So, which in each system frequency is quite similar to each other.
Yeah, so I guess that's my question is why though? Like, right, why are we at 59.5 and the East Coast is at 60.5 instead of just making them the same so they can connect them? Like, is there just something in the way the stuff was built, or?
Yeah, there's the way the thing was built. Like, this goes back way back in history of just happens right? The population center was on both coasts. So you're sort of building from coast inwards. And then building transmission line got very expensive. The system got way too large, too unwieldy to control. So then sort of just stop building once you get close to the middle. Historically, that's the way it happened. And if we want to build a lot of transmission lines, there's nothing stopping us from connecting to grids except cost, I would say. And then Texas is their own thing. Like there's complex legal cases for Texas, such that Texas just that we are not going to be part of your grid. Right? We're going to be our own grid, so such that I don't have to listen to federal regulations. That's right. There's complicated legal things for Texas, but it's mostly historical.
So if Texas had another blackout and they, like down the road, wanted to connect to the east or west power grids, would they be even able to do that since they're maybe slightly off on phase angle or on frequency? I'm sorry.
No, so once you build enough lines, you're naturally balanced, right? So you have enough transmission lines, you'll balance. So few transmission lines is bad because those few transmission lines cannot synchronize two huge grids. But let's say if you give me 10 gigawatts of transmission lines between Texas and the Eastern Interconnect, sure, they can synchronize. It depends on how many lines they want to build. So building a few lines probably won't do much, will not do much. But if we have sort of massive infrastructure building between Texas and the other interconnects, sure, they can synchronize. It just depends on, it's hard to say whether that will happen. I think sort of the easy answer how to prevent Texas blackout is just to connect to other grids. But once you look deeper, there's sort of both, there's engineering, economical, and sort of social issues, saying that may not be the sort of feasible solution, right? Maybe better control and more storage may be the way to go. Right? Maybe not, building 10 gigawatt transmission. Okay, any other questions about the system connection?
So then it's got to be pretty complicated because like we get power from Canada as well, right? And so, I mean, do we do anything with Mexico? Because like I know back in, I don't know, it was early 2000s, we had a huge blackout on the East Coast because a power plant in Canada went down, if I remember right, that supplied the East Coast. So
no, it's power plant in Ohio. A line in Ohio went down. Oh, took out Canada. I was in Canada at that time, took out Ontario, but the line was in Ohio. Yeah.
But there is a connection then?
Yeah, so the North American grid, so Mexico is not connected, but the North American grid, so the Canadian and the American grid is 4 grids. Western interconnection, so obviously who we are. So BC, Alberta, and the West Coast. Texas, Eastern interconnection includes everything from, let's say, the Rockies to, I don't know exactly where it is, but from the middle of the country to the East Coast, and Ontario, and then Quebec. So Quebec is its own grid, Texas is its own grid, rest is sort of divided down the middle, east and west. So blackouts is a very complicated subject. Whether a big grid is more prone to blackouts or helps to prevent blackouts, the answer is often yes to both questions. So we'll, if we get there in the end of the course, we'll talk about blackouts or larger systems. But for now, we're going to concentrate on one generator and see how that one generator. We'll treat the grid as an infinite bus. Right? So if you look at this as our grid model as just a generator looking at a voltage. Right? So we're just generator looks into a voltage. So we'll stop here today, but we actually don't have much to go for the grid. It's basically the same equations, except a sort of slight modification, because now you have, instead of a term, we have sort of another voltage to look at. So the reference becomes the grid, voltage becomes the reference, but most of the equations stay the same. Right? So we stop here today. And then next Monday, we'll finish synchronous generation. Then we'll go to transformers. Right? Okay, so no questions. I'll see you next Monday.
Thank you, Professor.
Thank you.
Thank you.
Thank you, Professor.
Thanks.
I have a question.